In this video, we'll be discussing the binomial distribution. The binomial distribution gives us the probability of observing a certain number of successes after a certain number of trials. Each trial must only have two outcomes with a fixed probability for each trial. A famous example is a set of coin tosses. Suppose we flipped a fair coin 3 times and wanted to know the probability of getting one head. This can be modeled by a binomial distribution with P, the probability of success, being equal to 0.5. Because on a fair coin, the probability of getting heads is 0.5 and the probability of getting tails is also 0.5. 2, we have the number of trials, which in our example is 3. And lastly, 3, we have K, the number of successes, which in our case we like it to be 1. We want one head. And so what is one configuration of getting one head? And so we can toss a head on the very first toss and then 2 tails following that. So if we were to compute the probability of this, what would it be? It would be the probability of getting head, which is 0.5, or P, we could write it more generally, times the probability of 1 minus P, which is the probability of getting tails, which is also equal to 0.5. 1 minus P. And so you see here that this is equivalent to P times 1 minus P squared. What's another example of a configuration we could have? So another example would be getting 2 tails followed by a head. So what would the probability of this particular configuration look like? It would look like 1 minus P times 1 minus P times P, which is equal to 1 minus P squared times P. And notice that there's one other configuration that we could have. We could have a tail followed by a head followed by a tail. And then the probability of this configuration would be 1 minus P times 1 minus P, which is again equal to P times 1 minus P squared. And so if we were to generalize this, it would simply be the number of times that we want head to appear. If we were to generalize one of these probabilities, it would be the number of times that we want head to appear or to get a success. In our case, this is K. So it is P raised to the K power times 1 minus P, which is the probability of failure, raised to the number of trials N, subtract K. And you'll see this is the same as if we were to fill in the different probabilities. This is the same as 0.5 raised to 1 times 1 minus 0.5 raised to 3 minus 1, which is 2, which, if we generalized it, is P to the 1 times 1 minus P squared, which is exactly what we saw above. But notice we need to actually add these probabilities from the 3 configurations. So if we were to add these 3 configurations together, we would actually get 3 times P times 1 minus P squared, because there are 3 separate configurations. There's 1, 2, and 3. So what is a way in which we can get this number 3 in a more mathematical way rather than writing it all out? And this is actually in mathematics known as a combination. And so a combination is written as N choose K which is equivalent to n factorial k factorial times n minus k factorial. And so just to show you in our example, I'll quickly write n is equal to 3, k is equal to 1, and p is equal to 0.5 in our example. So we have 3 choose 1 is equal to 3 factorial, 1 factorial, 3 minus 1 factorial. It's equal to 3 times 2 factorial. 3 factorial times 2 is equal to 3 times 1 times 3 times 2 times 1 over 2 times 1 is equal to 3. And there we go. Mathematically, we were able to get the 3 that we need. And so if we were to write out the whole entire equation of the binomial distribution, we have the probability of getting k successes, knowing that we have n is equal to 3, or knowing, I should just write more generally, knowing having n trials, each with a probability p is equal to n choose k times p raised to k times 1 minus p raised to n minus k. And so this is the generalized version of that example that we just did. And this, in fact, is the equation for the binomial distribution. And so, thanks for watching.